Hello class, welcome to Geometry Lesson 7.2, which is all about similarity transformations. By the end of this lesson, you should be able to determine whether figures are similar. So let's jump right in with example 1, where we are going to graph a composition of a rigid motion and a dilation. So hopefully you remember the word composition from back in chapter 3. Composition is when you do more than one transformation to a figure. So you change it in more than one way. And then remember a dilation, we learned yesterday, reviewed yesterday, because you've known that from the past, but a dilation is where you take a shape and you make it bigger or smaller. Okay, so today we're doing a composition of a rigid motion. Remember, a rigid motion are reflections, rotations, translations, where the figure stays exactly the same shape and size. And the dilation will take that rigid motion and enlarge it. So if we look at this picture, we start at ABC. Okay, so ABC is that black triangle there. And our problem says if line M is represented by the equation x equals -3, what is a graph of the image? And then we have the composition of capital R means reflection, with a dilation with scale factor of 0.5 on triangle ABC. So that was probably a lot of vocab words that you're trying to dust the cobwebs off of and remember. So let's talk through this. We have triangle ABC, that black triangle. And remember, when you have a composition, it's that weird looking notation with the open circle between two things. Remember, you start with the second thing listed in that parenthesis. So we're going to start with the dilation. So our dilation is 0.5. So I can multiply all of the vertices by 0.5. So in order to get my new C, my C prime, I'm going to do 0 times 0.5, or 0 times half, and that's 0. And then 10 times 0.5, or another way to say it is 10 divided by 2, right? Multiplying by 1/2 is the same as dividing by 2. So 10 divided by 2 is 5. So that's how they got C prime to be right there. A, if I said half of 2, that would be 1, and half of 4 would be 2. So that's how they got A prime there. And then B prime, half of -2 is -1, and half of 8 is +4. So that's how they got the blue triangle, A prime, B prime, and C prime. And they connected the dots. Then they did the second part of this transformation. Or the second part of the composition, which was the reflection over line M. So they said, okay, here's B prime. It is 2 units away from my vertical line of reflection. So I'm just going to count 2 units in the other direction. Here C prime is 1, 2, 3. So I'm going to go 1, 2, 3. Same thing with A. A is 4, so we're going to go 4. And these new dots form A double prime, B double prime, and C double prime. And that is my final answer. Okay, so remember, compositions, you're going to move it more than once. All right, so then given that information, I want you to try this problem. Okay, so you have the vertices of a triangle XYZ are X 3, 5, Y -1, 4, and Z 1, 7. And I want to know what is the graph of the image once it goes through that composition. Remember, the capital T stands for translation, and you simply add those numbers to your current X and Y values, okay? So good luck. All right, hopefully for this problem you did the translation first because you remembered with a composition you start with the second item listed in the parentheses. And when you did that, you had x prime, y prime, and z prime at the same points that I have listed on the board. And then after you did that, you took those new points and you did a dilation with a scale factor of 2. So you multiplied every number by 2. So you should have ended up with x double prime at 8, 6, y double prime at 0, 4, and z double prime at 4, 10. All right, so then example 2, we want to describe a composition of a rigid motion and dilation. So last time, on the last problem, I gave you the transformation and you performed it. Now I'm giving you the image of the transformation and I'm asking you to tell me what happened. How did we go from the, in this case, the black triangle to the red triangle? So is there a composition of transformations that maps triangle XYZ to triangle JKL? And explain. So if we look at both of the triangles, the two triangles appear to be the same shape, okay? They look the same. They have that one larger angle and a flat side, right? But they are different sizes. And they're also positioned differently, right? One of them's kind of standing upright and the other one's facing down. So that means that there's at least two motions that occurred. One would have to be a dilation, right, to change the size. But we have to think, is this a translation? Remember, a translation is where it just slides. It doesn't flip or rotate. It can't be a translation because it needs to not be facing the same way. A reflection is when it just flips over. And if we just flipped it over, it would either be facing kind of, let's see, if we flipped it over, let's just quickly look at how that would not necessarily work. It would look like this if we reflected it over the x-axis. If we reflected it over the y-axis, it would look like this. So you see how neither of those matches the orientation of the the red triangle. By orientation, that's another way of saying the way it's lying, like on the graph. It's not the same way. Okay, so translation and reflections don't work. That means this has to be a rotation, right? So since it starts in the upper left quadrant, or the first quadrant, and a corresponding vertex, so they chose K in JKL, is in the lower right of the third quadrant. So they said Y is in the upper left, K is in the lower right. So it appears that it has been rotated and it has also been dilated. So then if we look, we have to think about, okay, how would it have to rotate? If it went through two whole quadrants, that means it's rotated by 180 degrees. Remember, each quadrant that it goes through has 90 degrees. So in this case, it has rotated 180 degrees and it was dilated. So I would say, okay, you have to rotate it 180 degrees and you have to dilate it. So then you'd have to compare the sizes just like you did in yesterday's lesson, and you'd find that the scale factor is 2. If I compare, this is 2 long, this is 4 units long. So the origin is the center of dilation because the lines connecting the corresponding vertices are all concurrent there. And I feel like when I say that, you guys don't know what I mean. So let me say maybe an easier way to identify that the origin's the center of dilation. Remember yesterday when we used a point as the center of dilation? We would have to have a point drawn somewhere on here, and we don't. And if we used a vertice of the triangle, that means one of the vertices wouldn't move between the rotation and the dilation. So like point X, let's say, would appear on both of the triangles. If you go back to yesterday's lesson and look at that example, you'll see that one of the points stayed the same between the two rectangles when we did that example. And then let's talk about when you have circles. So circles are kind of unique in a lot of ways, but this is one of the ways that circles are unique. If you think about it, all circles, no matter the size, have 360 degrees in them, right? So you can't change the look of a circle because there's only one way to really draw a circle. There's different sizes, but like with a pentagon, you could draw it many ways, right? You could draw both of those are pentagons, but different, right? There's only one way to draw a circle, and that's to draw a circle, the shape, the round. And something unique about circles is that they're all similar. Well, correction. They're either similar or congruent. There's no other relationships between circles. They're either similar, they're different sizes, or they're congruent. They're the exact same circle. There are some other shapes that also meet that criteria, so I want you to think, is a square one of those shapes that squares would always be similar? Would that be true? Is there more than one way to draw a square? Or is it like a circle where it's either going to be similar or congruent? So think, are two squares always similar? And I don't want you to say no because they could be congruent. I want you to say, if you say no, I want it to be because of the pentagon reason, where there's a different way to draw it, okay? So go ahead and think about that. All right, hopefully you said that, yes, squares are always similar. You can't change the angles that make up a square, and you can't change the side lengths that make up a square, right? So that means that you're left with the same type of shape every single time when you draw a square. And so they're either going to be congruent or similar. So that pretty much sums up everything for today's lesson. If you look in your book, you're going to find a few more examples. There are some things that I'm not going to make you do. I won't make you try to figure out the composition of figures without a graph because I think that is, I just don't think that's maybe the best use of our time. So all of the problems should be like this, where it's on a graph, or it'll be, I'll give you a picture and I'll say, would this be like a reflection and a dilation or something like that, okay? So if you have any questions, please be sure to reach out for some help, and I'd be happy to assist you. Have a great day.